I will demonstrate, it's okay, you hear me? Yeah. I will demonstrate how fractional order concept permitted us to explain characteristic behaviors of rectilinear ball in manual interception. Before to start, I would like to talk about a paper a bit alone in the literature, written by Montaigne et al. They run a quite simple experimental setup. It was 3 initial hand positions possible, -35, 0, and +25. And participants had to catch 3 kind of ball trajectories with 3 angles of approach different, -4, 0, and 4. So what about the results? What we are here is the average time series of the position all over the time. The first thing that you can observe is when the initial hand position was -35 or +25 centimeters, participants moved differently to catch the 3 different ball trajectories. That's what we call angle of approach effect. When rectilinear ball trajectories converging to the same point give rise to different kinematic patterns. But that results were largely demonstrated in the literature. The more surprising thing is the reversal movement. It's when the initial hand position corresponded to the future arrival ball position. For that, to catch a ball coming from the left, people operated a first movement on the left to after be back at the initial hand position. And Montaigne et al. Is one of the only papers reported that result. So the first thing that we did is to run an experiment to see if we observe it as well. Oops, sorry. Okay. 11 participants sat down in a dark room in front of a graphic tablet and interacting with it, sliding stylus on a rail. On the tablet, many virtual balls appeared with different kind of trajectories. It was 4 ball departures possible, -15, -5, +5, and +15 centimeters, and converging to 7 ball arrival positions. 4 ball speeds were possible, resulting in 112 conditions performed in 3 blocks. About the result, I will present the result in 2 parts. The first part about the angle of approach effect. It's concerning trajectories not arriving in the 0 point, because the 0 point corresponded to the initial hand position of the participants. And the second part will be about the reversal movements. The 4 trajectories, starting from 4 different ball departure positions, but converging to the 0 point, the initial hand position. First of all, I will present the result about the ball speed 1, but we observe the same qualitative results for all the ball speeds. So on the first panel here, you have the 24 different trajectories, not arriving in 0. And here, you have the kinematic patterns on the on the axis, how they slide on the tablet all over the time. The first thing that we observe, it's a systematic angle of approach effect. I mean that if you observe the 4 trajectories arriving in the point -15 centimeters, participants move differently each time. It was not the same kinematic pattern. And those differences were the same for the 6 ball arrival position. But the other thing that we observe, it's a clear trajectory effect on the initial time. The circles here represent the ball position when participant initiated. What we can observe, it's not each time the same position, and some trajectories, especially the 4 crossing the x-axis, and arriving close to the initial hands position led to later initiation time. That one, that one, that one. And kind of a pattern is observed each time. It's kind of systematic. About the reversal movement. Here again you have the ball position evolution all over the time, and here you have all the trials. On 28 trials, we observe 180 reversal movement. It means an excursion more important than 1 centimeter. So it was not systematic, but we observed it. More in the details, we observe a stable rate relative to the factor ball speed. Always the rate was between 30 and 40%. But more, we observe a significant differences relative to the factor ball departure position. For the trajectories with a more external ball departure position, minus 15 and plus 15, it was a rate of 45% of reversal, and for the more internal ball departure position, almost 25%. To go further, 94% of reversal were in direction of the ball departure position. To understand that graph, here you have the reversal amplitude in centimeter, and here you have the initial time at time to contact. So the time to contact at initial time. Here you have the example of one trial. A participant starting on the 0 point, for a ball departure coming from the left, going on the left first to be back and catch the ball. If you take the initial time and the more external amplitude, you get that square. So here you have representing the 180 reversal movement. And what we observe is that the reversal amplitude depends on the initial time. More you initiate early, more the amplitude will be larger. So to sum the result part, we observe a systematic angle of approach effect, a systematic trajectory effect on the initial time, and about the reversal, in the 180 reversal observed, initial time had an effect on the amplitude. So now I will talk about the model. Before we start, I will talk about the series, the Taylor series. Taylor series define that XB0 is the current ball position on the axis displacement. If you take in account the velocity and the time remaining, the first order, for straight trajectories, you get the arrival. It's XB1. If it's a curved trajectories, and you take into account the acceleration and also the time remaining, you can have the future arrival position. And so on if you increase in the order. In the literature, 2 different models were developed, quite close, but including 2 different information, the 0th order model and the 1st order model. So if you look, if you simulate a model, the 0th order model, it means that the attractor all over the time will be XB0, the current ball position. So the model predicts that you will go on the left first if you need to catch that 6 trajectories, the red one for example, to after be back on the right if the ball converges to the right. So you get the angle of approach effect, but it's not the pattern that we observe in our data. About the 1st order model, you don't see the red, but it exists as well. But for 4 trajectories arriving to the same point, if you take into account the velocity, the attractor all over the time will be the same. So a model like that can't predict the angle of approach effect. So here is the fractional order concept. Here you have a trajectory starting in minus 15 centimeters and going to plus 15 centimeters. So if the attractor is xb0, it will attract to you here at the beginning and sliding to here to the end. If you take into account the velocity and the time remaining, so directly, you get xb1. And xb1 will not change all over the time. So the attractor all over the time will be xb1. But why not consider a continuum between 0 and 1? Putting an alpha in front of the velocity and the time remaining. As Reinoud said, we will take as an example alpha equal to 0.8. So it's not exactly xb1, it's not xb0, it's closer than xb1, but it's not that. And like that, you have an attractor sliding all over the time to the arrival point of course, but not exactly xb0 and not exactly xb1. And like that, you can have different trajectories with the same alpha, but not with the same attractor evolution all over the time. And fractional order cassette could capture the angular approach effect. To go further, I'm back on the initial time. Do you remember I was talking about the 4 trajectories leading to systematic later initial time? If you put here, you point the value of xb1 at that initial time, there is no pattern. But if you do the same with the attractor all over the time, if alpha is equal to 0.8, you can see that, as for the other, there is a dead time when participant never initiated during this time period. But you can also maybe distinguish a non-action zone. Of course, if the attractor is far than you, you are going to initiate really early because you have to move if you want to catch the ball. But if the attractor is specifying a zone close to your initial hand position, there is no reason to move. And that's why the 4 trajectories crossing the 0 axis but going close to you, the value of xb alpha, if alpha is 0.8, are going to have a value close to 0. So there is no reason to move if the attractor is specifying a zone close to you. So what about our model? The model is the model explained by Reinoud before. You have just saw it's velocity required to do minus your current velocity. And here you have the results. So the model is triggering on the asymptote. It means that it's starting when the value of the attractor is exceeding the asymptote value. And as you can see, the systematic angle of approach is captured. But now the question is, what about the reversal movement? To explain how the model is working with the reversal movement, I have to be again back a bit on the initial time. Because it's the first moment that something happened and we are sure of it. Of course, that it's the mean of the initial time, but not all the participants initiated at the same moment. So, if you get that 2 trajectories different, you can observe the distribution of the initial time. That you see that on trajectories there is not a lot of distribution because on the blue point it means that 10% of the trial were initiated before. And after all the ball is 20%, 30, etc. to the end. And what you look is that for the specific trajectories leading to later initial time, there is a larger distribution. So if you put it on you're confronting that result with the value of the attractor all over the time, you can again develop the idea of the dead time and the non-action zone. But of course, you will have different asymptotes, representing the different kind of sensitivity of people at the moment. So, I just have a look about, you remember it was 4 trajectories converging to the 0 point, the initial hand position. So for that trajectory, xb alpha, if alpha is 0.8, means an attractor evolution all over the time like that. 4 trajectories. So you have 4 attractors. And if you simulate the model, you can see that the two trajectories with the most external ball departure position, -15 and +15, crossing the asymptote, the first one representing 10% of the trail initiated, 20%, 30%, 40%, but not all. And for the more internal, it's just one cross. And more interesting, the model predict that you will have more important amplitude, a larger amplitude, if you initiate early. Because of course, if the attractor, the value attractor is that one, at that moment, the distance to do will be more important that if you wait more, and that the attractor is converging and closer to the end, to the arrival position. So triggering the model with the asymptote 8, 10%, 20%, etc., the probability to observe a reversal is captured. And more, the initial time influencing amplitude is also captured. So what does the fractional order concept do for us? An explanation of the systematic angle of approach effect, an explanation of the trajectory effect on the movement initiation, and an explanation of the reversal probabilities, I mean that sometimes you can do that but sometimes not, and why amplitude is dependent on the initial time. And now Remy